Simpsons, yeah, Simpsons is this approximation method to find the area, right?
Mm-hmm.
Have you started this part or you
No, what happened?
haven't, right? So that is a historical issues because before invention of the calculus, and people have no idea how to work out the irregular area. They can work out the square, rectangle, or trapezoid, but they cannot work out the graph, the area with which is this is question. So if you have the one side is irregular, right?
Mm-hmm.
Or is a different color. So that is this is a different way to study the calculus. Is to study integration.
Yeah.
So in order to find the area of this area under this curve, in order to find the area under this curve, let's do it properly. But from this side to the other side, you see?
Mm-hmm.
So the question is how to find this irregular area. So that is the question, right?
Mm-hmm.
And the Simpson method just tell you how to do it. Actually, there are two different approach. And one is just simply use this. I can give you several options. First is to divide. We use this rectangle to approximate the method, the area. So that you can see. We can make it into slices, right?
Mm-hmm.
And that's how we do that. So we can use the mean value of this height in order to find this area of each slice. You see, you can continue until last one. You see, until last one. So in doing so, we can argue that this area, can you see this is A1, is A2, and this is depending on how many A you have, can this is AN. So we from this one, we can argue that the area, the exact area, will be very close to the sum of this individual area. Do you agree?
Yeah.
Of course, there are some apparent difference, but depending on how to choose this width. For example, if this side is A, this side is B, right?
Mm-hmm.
Now, if you divide this into n times, so this width, can we call the h, or whatever? Can we use this as I don't know, it's a h, which is can we call this delta x? Can we call it delta x, right?
Mm-hmm.
This delta x is equal. So this is delta x. So in this equation, we know that for any area of this rectangle, A will equal to, because this is will equal to the height, right?
Mm-hmm.
Vertical to the height. Will equal to the height A multiply the delta x. Do you agree?
Mm-hmm.
And this height is also related to this function. You see, if this is equal to yx, okay. So what you can see, you can just use this mean value. You see, you can use this mean value. So of this called mean value. So you can use the y I multiply this delta x. Delta x is if you divide this into the n, so delta x can be written as b take a divided by n. So basically, we chop this area into n slices. Can you see?
Mm-hmm.
So this is basic idea to work out this. This is approximation method. So this I from 1 to n. See, so you just use n rectangle to approximate that irregular area. Okay. So that is the basic idea behind the Simpson method. Of course, if you go to detail of the historical, they have different approach. And so this one, if I just enlarge this part, if I just enlarge this nth slice, you see. So this one we have this time I only draw one of slice. You see, there's one of slice here. Okay, so if I choose the two adjacent edge, so this is one side. There's another one. You see. Okay. So if you count, this will be this will be A will be x1, A x1. So this was the x, this x can we say xk. So this will be x k plus 1. So this perhaps use this k. I use I as k, right?
Mm-hmm.
Doesn't matter. I use I. Is and this is ice. This ice x. This is I plus 1. Okay. In this case, historically, you have two choices, right? You can either choose this side as a mean value. You can either choose this side. Can we?
Mm-hmm.
Or you can choose the other side, right?
Yeah.
Let's just go to this, can I do another one? So if you choose the xi, then you always, there's always difference between these two, right?
Mm-hmm.
And should I say? So you can either choose this side. I just use same diagram. You can either choose this side as the height, you see?
Mm-hmm.
So in this way, you can either choose that the area for this nth area. So this is area I. So this is I. So area I. You can either use y xi. So this is this height. Can you see?
Mm-hmm.
This side you call to y xi, or you can choose other. You can choose this y xi plus 1. Can you see?
Mm-hmm.
So this is different method. This is a general approach. This is how to approach this area. Or you can use a different assumption. You can choose the y xi plus 1. Can you see?
Mm-hmm.
Of course, visually you can see the difference. But however, if the n is large, you wouldn't be able to notice the difference, right?
Mm-hmm.
So this is so in practice you can use different approximation. More accurately, you can see. Alternatively, you can even use another approximation, which is even better. That is one of them. Can we just draw this diagram again? So here we just focus on this particular slice here, you see, right? And again, we need to use the approximation to describe this irregular area. Okay. So in this case, apart from these two methods, we can also make it more accurate. So this is xi, this is xi plus 1. We can, instead of use this approximation, which both are not exact, right?
Mhm.
However, if we choose this trapezoid, so that is how that is can we use this? Can we use this straight line here? Can you see?
Yeah.
Then we should reduce this error. You agree? So this is even better, isn't it? So if you use this side, this is y, this is x. Again, this height is y xi, and this height is y xi plus 1. Can you follow me?
Mhm.
So instead of looking for this rectangle, so this is in the first approximation, we use this rectangle as approximation. Okay, this is approximation, and this time we'll actually we'll use more closer. The model is even better approximation. Do you agree?
Mhm.
So this time we just focus on this. We use this trapezoid to represent that actual curve. So therefore, this is closer to the true value of this slice area. Can you follow me?
Yeah.
So this is even better choice. So Simpson, I forget which one Simpson used, but Simpson's method is just one of these three, all right? So this is best one. Now in this case, can you write the area? You have multiplied delta x. Delta x is the same. Can we say that delta x is always equal to the interval b take a divided by a number of cut of slice, right? However, can you work out the area this time based on this choice, based on this trapezoid area instead of the rectangle? So what is AI? So this is the ice. This is ice area. So this is also the ice area.
It's x, y, x. I'll write it down.
Delta x is the same, right? Delta x is the same. Half, right? Half. Yep. That's right. So if I probably go to next page, it's a bit crowded here. So if I just focus this area, yeah, that is the key part of this method, Simpson method. So basically, we need to work out this area. Yeah, I notice you use the sum of the two areas. That's fine. And so basically, we are trying to calculate this height is y xi. This is y xi plus 1. Okay. Now this is delta x. Okay. So this xi is xi plus 1. That is our x-axis. So this area in this case, you just copy yours. We can also use trapezoid method formula, right? Trapezoid formula is a sum of these two, xi plus y bracket x I plus 1 divided by 2, right? And multiply delta x. So this formula should be equivalent to yours, all right? Can you see that? You just factorize. You factorize delta x. Okay. You see? So that is the formula the Simpson method used. So in this way, we know that that is original. So that is a true. This is a true. This is a true curve, right? That's probably the true curve. So these among these three approximation, this is the best. Yeah. But
Yeah.
So therefore, we can argue that in all cases, the true area can be approximated as the sigma of this sum of these slices, in which you have three choices to determine I from 1 to n. Can you see? So that's it. That is the Simpson method.
Is that Simpson's rule?
Yes. So you see, this is graphical method to obtain the integration. Actually, if you have if you know how to do integration, if you know the function, so if you know the function, so this, can we just return to the case? If you know this case, if we know the integration, the area should exactly equal to the integration from, it's called definite integral from a to b and yx dx. So that is the analytical formula. So if you know the function y, we don't have to use this approximation method. All right. Simpson method was used to as a approximation method to calculate area. Because the reason you start this part, because people believe that people who study specialist maths will eventually choose a science subject, in which they have to use approximation method to solve the practical problems, right? So that is why, in addition to teach you the formula for integration, they also teach this Simpson method. This one, can we just show you? So your method is equivalent. Can you see? If I just factorize delta x, right? You factorize x, you got y xi, can you see? Plus half, can you see? So you got delta x, so you got there's a difference between these two, right? That is a the difference, that is I plus 1 minus y xi divided by 2, all right? So this message, this is the same. So this formula is the same. That's some remark here. So if you apply, you can apply this to solve any questions. If you want to, do you have example? Do you want to try this? Can we just take example to show how to use this formula? Can we just let me see. Let's find more space here. Can we work out? Can we show you example how to use this formula, or how to use the method? All right. For example, let's calculate the pi. What is a pi? All right. Calculate pi. So this is a very important. This is very interesting example. Can we consider this unit circle? Right. So this unit circle, therefore, and let's go to first example. So how to calculate the pi? Use this Simpson method. Can we call this y, this x? Do you remember the formula for the circle? So this is 1. Can you see this is 1, 0. So this is 0, 1, right?
Yeah.
So the formula for this one is x squared plus y squared equal to 1, right? Or if we just focus on this quarter, so y can be solved as a positive value, right?
Yeah.
Y take x squared and the square root. Okay, I'll give you a hint. So what you can do, you can slice this into several slices. Can you see? I can. This is the first slice. make it through, just simplify. Can we just simply slice that into the 4 equal slices, right? 4 equal slices. Of course, if you use more slices, the accurate is more accurate. The result will be more accurate, all right? Okay, now you have choice. You have choice to use this. Do you want to use you have 3 choice. Which choice do you want to use? So this, can we just label this one? So this is 0.5, right?
Yeah.
This quarter, right? This is quarter. It's quarter. Maybe I just use this quarter. So this is oh, sorry. So this is quarter. There's half, right? There's 3, 2, right? Is that
3,
right?
4.
3, 4. Sorry.
Isn't it 3/4?
3, 4. Yeah, 3/4. Yes, that's right. You're right. 3/4. And last one is 1. Okay. So here we got 4 slices. Can you see? So this is A1, A2, A3, and A4. Okay. Okay, you can try. How can we work out the pi, or how can we estimate the pi?
What was Simpson's rule again?
Yep, we go back to Simpson's method. Do you want to use this trapezoid method?
Yeah.
Okay, that is the best one. That is the most popular. This is Simpson method. So this AI is the sum of these 2 divided by 2 multiply delta x.
Yeah.
Okay. By the way, what is the total area?
Wouldn't it just be all of this?
No, the value. The value. What is the area for circle?
2 pi r with a pi r square.
Pi r unit is just r. You see.
Oh.
So can we say the quarter? So this 4. Can we say if we use this notation? So if we just work this time, we just focus on this this quarter. Can you see? We just on this quarter, so you can work out this this one. We got the 4 slices. So these 4 slices represent the A. So first we have to remind you A is equal to pi divided by 4, right? Because the total area is pi r squared, right?
Yeah.
Yes, that is a formula, right? That is a formula. One moment. X1, yes. X1 plus 1, yes. So what is your X1 to 3?
This is x1.
Yeah.
x2, x3, x4.
5. Yes, that's right. We have 5 altogether. Perhaps it's a, can we make a table? Otherwise you have too many numbers here. Can we make a table here before we go further? Can we make the table instead? How about y and x? Can you see? And how can we make this table? X and y, yes. So this is, can we call this is xi, can you see? It's yi. Oh, not this one. Y, yeah, I want to put xi, yeah, that is notation. So we have first one, so x1, y is 0, first is 0, right? Y is 0. And then the second is what? Second quarter, right? And the third is half. And we continue. So, yeah, probably we just pick up this number from this table and without put all numbers in the formula. Is that all? 1, 2, 3, 4, 5, yes. So that is 1, can you see? 3/4. Can you work out this number first? So what is yes, 1, yes, that is first 1.
Yeah.
Okay. Okay. And then can we calculate this
Wait,
area?
not
Can you
fine.
calculate area? Can you calculate area? Delta x equal to quarter, yes. Okay. Yeah, you have 4 pieces area. How can you get 5? How can we get 5 area? Double check that. How can we get the 5 area?
Oh, I don't think this can. This doesn't.
Okay. Right. You can use the calculator to add them up.
Yeah.
So you have to appreciate how ancient mathematician work out this pi number. Very difficult, right? Just numbers.
It's equal to 0.194.
Yes, that is total area. Yes.
Mhm.
You have multiply 4 in order to get a pi, right?
Yeah.
If you multiply 4, what would be the result?
0.776.
Oh, quite different.
Hmm.
Something wrong with do you want to check up? Do some check. Let's see. The y value first is 0. The second is yeah, you are right. That's
Oh, I see. I just did all of them as 1, but this should be 15
aha.
over 3. And this
Square
should be-
root, right? Inside the
Yeah.
square root, inside the
And
square
this
root.
should be square root 3 over 4.
Oh, yes, that's right. That's right. You have to use not the difference between square, but the square root as a whole, right?
Mhm.
It's quite different. It's quite different. Yeah, it's different between two square roots. That's right. You're right.
It adds up to 1/8.
Pi equal to 1/8.
Mhm.
1.18.
Well, no, the total area is 1/8, and then pi is equal to 0.5.
Oh, that's quite different, right?
Mm.
How comes that different? Let's see. Did you delta? What is did you multiply delta for? This is your formula.
Oh, delta x as well.
You multiply here half. And that is the sum of these two. Oh, not the difference. Sum. Wait a moment.
Oh,
Should be the sum, not difference. Is it? This is the sum, not difference.
and I also forgot the delta x.
Aha, this sum. Yeah. Yeah, that is a different. This is a number is very sensitive to this result. Formula is wrong. Okay.
Mhm.
Do you want to try again?
Yeah.
At least we can get 3.1, right? Or 3.2. Yes.
Oh no.
At least larger than that number, right?
Yeah.
Because you got a sum.
When you times it by 4, you get 2.44, which I think is close enough to pi.
2.44. Yeah, probably that is what we can expect it. So what do you think? How do, yeah, go on.
I did a calculation. 2.94.
Not bad, close to 3 now, right?
Yeah.
Let's go to 9.3. Yes, write your result. So that is what your pi? Approximately equal to, right? 2.7, 2.9. Yes, okay, not bad. Close to 3, right?
Yeah.
Close to 3. Now, question: how can we improve this calculation in order to get a better result? That is if you can answer this question, you know what are you doing.
We should be using a definite integral, I think.
No, you jump to there's not, well, the definite integral, you have to know the function, right? Of course, here we know the function, but pretend we don't know the analytical integral formula method. The very important thing because here we only use, so in this case, the n is just 4. Do you remember?
Yeah, if we make n bigger, then it'll have smaller.
That's right. So in other words, if we can, I just explain to you, this is the key part. So if you can use a smaller slice, can you see? If you can use a smaller slice, can you see? And everything we're getting closer, can you see?
Yes.
And it could double, it would not double, triple, okay? Triple these numbers. And then we should be able to get a better result. So therefore, you can see that if I draw the graph, this trend line, so this here is that. So this is, let me see. So this is y, this is a value, so this integral, can you see? This is pi, can you see? This is just the actual pi value, is pi value. So if I increase, if it changes n, so at the moment n equal to 4, right? Now if you use 8, I go to 12, or even large number, so the result will be different. If we draw this distribution, that it could be so the result, your result will be distributed like this one. Let's just use different. You see, and like that, okay. And then if you increase, I will get that, or probably they even overshot, right? Okay, overshot. But eventually they will you will reach to that after they were oscillation for a while, maybe, right? So that will. So compare with if you just use 2, that could be terribly different, right?
Yeah.
So the reason we started the Simpson method is to appreciate that if I just use an accurate formula in which delta x is actually approach to 0, right? So n when n equal to when n approach to infinity, and this delta x is approach to 0. So you have to really appreciate that. So that is why if you wish, you can use this method to just double the number of n. Of course, you have to take more time, but that is expected outcome, the improvement. Okay. Do you have the? Can you find the question we can solve in this chapter?
I lost access to my textbook.
Okay, let's just find another question you can solve. Simpson method. Metric. This is math B, isn't it, right? Math C or math B?
Math C.
Let's see. Let's often introduce this before they use a formula. Oh, doesn't matter. I invented one. You can do. This time I give you another function. So this time, can we try? Can we try the Probably this time we compare different formula this time, all right? So this time we will give you this example 2. This time we got a quadratic function. We got y equal to 2x squared, and that's it. That's it. And this time we know it's parabola. We know it's parabola, right? We know it's a parabola, and maybe. So it's just graphical for this method. So we got this parabola like that. Okay. So can we work out the area under this curve and use the Simpson method? Is y, and from the this is from 0.2 and to 1, or from 0 rather, from 0.0. Can we do this one? This is 1. Okay, you decide. You can we use how many slides? Can we just give you a slide number of slides? One moment. So we're trying to work out this area under this curve. Can we use this time? How many slides we use? Can we just try n equal to 4? Just cut into 4, right? Cut 4. But we have tried different method. So A is uses the area equal to Simpson method, right? That is y, y x I plus 1 plus, that is y, one moment, plus y x I divided by 2 and multiply delta x, all right? And the second, we use this formula, which is we studied. We just use the y x I, just use this I, is a simple method. Can we just use y x I multiply delta x? Okay, can you try to see the difference between these two? Oh, one moment. This point, yeah, it's quarter. You're right. This is not right. Yeah, use quarter. That's fine. It's divided into. Let's do it properly. So the half. To be true, this one. It's confused. So the half is 0.5. This 0.5. Yeah. 2, 5. Yeah. So delta x, so here's delta x, 2, 1. Oh, all fractions.
So that's for method
The
A.
first A is what?
I think it's 10/16.
Okay. Just wondering, how did you, can you explain to me how did you work out this formula? This formula, quarter is a delta x, right? Okay, so the first one will pick up this value, right?
Mm-hmm.
So this is quarter as well.
Yeah.
Do you think this quarter?
Oh, it's a y value. Yeah. No.
The y value, yes.
Yeah.
So you have to. So this is not. This is not a quarter. This is not a quarter.
Mm-hmm.
You have to substitute that, right? You see.
Yeah.
So this particular value is y equal to x equal quarter. So it's a 2 multiply quarter square, right?
Mm-hmm.
Yeah, you can put decimal, doesn't matter. You want to do it. Mhm. Okay.
This equals
Oh, yes, nothing larger, right?
Mhm.
Okay, finally, can we use this? Can we use the formula? So the area, can we use this formula? So the area can be written as integral from 0 to 1 and 2x squared dx. Do you want to try? Can you work out this
Yeah.
integral? Definite integral. Oh, that's quick. That's quick. 3, yes. 3. Okay, can you compare which is closer to this value?
I think it's this one.
Yeah. So what can you use decimal to compare them? It's very all close to. What is a decimal? Can you use a number? Yeah, 47. Yeah, 0.47. How about this one? Just pen. Wow, one is overestimated, right? One is underestimated. So that is yeah. Certainly, you know that why we have to learn both definite integral and also Simpson method.
Yeah.
Because you can look at back that's what happened even for computer. But of course, when you actually even today we still use the Simpson method. Do you know why?
No.
Because computer cannot do the analytical integral. So therefore, if you want to do integration in your research, the computer always rewrite this integral. They know this integral, but when they actually do a calculation, they just use the Simpson method. Although in this calculation, the number can be extremely large. Okay, here we only choose n equal to 4, but if you use a computer, you can simply go to 1,000 or even larger numbers. And also, the larger the number, the longer the time for computer to work out the result. So you can appreciate that this Simpson method is still taught in the high school.
Yeah.
Okay. All right, I will save this part. Okay. Can we stop here now today?
Yeah.
Okay, I'll see you next time.
I'll see you on Friday.
Friday, okay. See you.
Yeah. Thank
Okay.
you.
You're welcome. Goodbye.